automation, analytics, SCADA for energy optimization. We'll be following many of these set of webinars, which would be under the series of asset management, as we spoke about the last time, and this is one of them. So what we'll be doing this particular webinar is that we will be speaking about how cable health indexing is kind of a tool which helps many utilities out there and the IPPs when they actually want to invest in their feeder and the cable section lines. Now, apart from that, we'll be also touching upon how Scope OrxaGrid tries to, tackle this particular problem or hunt the solution when it comes to any of the projects that we handle. And apart from that, what are the outlooks which we do give in the under the gambit of asset management? Okay, so this is what is going to be the content of the entire presentation. We'll be speaking about what are the requirements when it comes to the customers and the projects which are being floated into the open market, where various big players who want to understand their utility threats when it comes to cable and the feeder line, because they are the major asset when it comes to the solutions where you want to make sure that the overall outage of the system is zero. And since we want to achieve a system which is not having any outages, blackouts, and blah, blah, what we want to do is that we want to assure that whatever requirements that do come from a certain project or the pain points which do come from the customer interactions are directly catered to in a given business. Again, as I said before, seeing from the vision point of view of the asset management that we have on the OrxaGrid side, we try to map it into the work or the implementation plan that we develop across our customers. These are the standard set of procedures which we try to implement, which includes technical and commercial responsibilities when it comes to the projects which are being handled by OrxaGrid/Scope, and using the defined plan of implementation, we define the tool sets which do help us in implementing any AIML set of tools for developing health indexes for cable and feeder lines. On the basis of the tools that we do use, we do define what should be the outcomes and the deliverables. And in order to give those deliverables to our customers, you will be able to learn in this particular webinar that what are the kind of bottlenecks which normally utilities do face. If not, you have already been engaged in such kind of activities, you will be able to be sure about the fact that what bottlenecks you could possibly anticipate in order to make sure that if you are going for an AIML project in the direction of prescriptive analytics for cable health indexing, what should be the anticipated challenges and how you should cater it. Again, what are the bottlenecks is something which are the issues that I would be speaking about. But then again, what is the outlook? So once you have solved these set of issues which you have in the data management, you would definitely want to know that what is the comparative outlook when it comes to the solutions that Gap offers. Gap is, as we told last time, is nothing but a software solution offered by OrxaGrid, and that is a web SCADA solution in where you can actually envision and visualize all the set of cable and the feeder lines which you have in your substations, and along your entire cable network, you can understand where exactly the fault is lying. Okay, so going back to our previous webinar on the same lines, we do always stick to the set of visions that we do set across any project requirements or slash customer requirements are the challenges in providing optimal services and the return on investments when it comes to any cable investment project. Now, again, we want to be sustainable, we want to be affordable and reliable, which is what I said in the last time, right? So what I mean by saying it is that it could be any set of cables. For example, I'm taking a use case of underground cable, but if I take the case of an underground cable, we want to understand that whether integrating these kind of solutions into the system allows capability of expanding it to EV solutions which are already there in the picture. And can we also add distributed generative sources in the entire system? which is one of the first use case when it comes to any cable health indexing solution that you'll be seeing in the market. Now, again, if I fix myself towards underground cable and I fix myself to underground cable because of the fact that underground cables are the major issue when it comes to the accessibilities and complexity in its own network. And in that case, if I want to make sure that, okay, a renewable based solution is also coming into picture, because that is what is going to be the overall integration and scaling up of the power generating sources in the future. Considering the solar, the wind, the biomass, and all, we do expect the fact that if the overall solution has to be sustainable, and considering the fact of underground cable in itself comprises of many complexities, but still we want our solution to be more sustainable in its definitive terms. Again, it should be affordable. Underground cables are not something, or aerial cables, if I have to be more, set specific, they are not easy to be accessed, and the data can be actually pulled out of it. So your solution, which anyone should provide in this particular segment, has to have the affordability in itself. Again, reliability is something which any utility would probably demand. Okay, so this is how we start. We try to deep dive into understanding that how exactly the market is growing in this sector. So the first step after defining that, okay, the vision of OrxaGrid and scope is moving towards defining a sustainable, affordable, and a reliable solution, we are more keen towards looking, and not we, I mean, any utility or anyone who is present in this particular forum is more importantly looking into the fact that whether this particular solution is having a market or not. So if we just do a literature survey and we try to find out that how exactly the power and control cables are placed in the market, you can see that the overall regional statistics which actually do come out from the Asia Pacific region is somewhere around expected to go around 110 US billion dollars around 2032. If I go across a global market value chain, then I definitely go towards 133.9 billion. And considering the fact that I want to be in the utility application segment, I can expect an overall market of around 250 billion US dollars. Now, again, what is the growth rate? The growth rate of implementing a power, and or I won't say just implementing, it's more about revamping also. So considering the entire revamping of these existing cables or laying new cables in the sectors where exactly the electricity has not reached in the segment like Asia Pacific, where countries like India or Bangladesh or Nepal, who are still struggling or trying to make sure that all the remote places are being provided by electricity, you can expect the overall OEMs in the power and control cable market to grow with a CAGR of around 7.1% till 2032. That is the case, you can understand that the overall market of development and deployment of power and control cables in this entire sector is going to be having more amount of requirements as we go. Considering the fact, you can also depend on the understanding of the health indices of these particular assets, right? Considering cable as an asset in itself, anyone who is deploying these investments, they would also want to know that what are their returns, and definitely if there are any OPEXs which are coming into picture, they are as low as possible. Okay, now delving for delving forward and forecasting, where do we see the all the requirements which are present in this particular sector? You can see that the overall market size by region in US dollars million, in million US dollars, is somewhere around 40 grand or something when it comes to the Asia Pacific market, which is pretty much something that anyone could expect when it comes to the overall investments which are going in this particular dimension, because of the very fact that all the cables, I won't say all the cables, majority of the cables which are lying in this this particular area are either too old or they do require high amount of OPEXs in maintenance, or they require replacement if the particular case is not definitive when it comes to giving the electricity with minimum number of outages or load shedding. In which case you can expect and you can see the trends that they are going right from 2019 to 2022 in an incline phase. If it is inclining with a CAGR of 7%, which I was mentioning in my previous slide, you can expect that there might be there is a possibility with the 7% of CAGR that it might go to a 250 billion US dollars, as I was claiming in my previous slide. Again, the fact over here is not towards seeing how many cables are being laid, but towards seeing that how many cables we can retrieve from failing or getting into a replacement or getting into a fault. So that is the whole idea behind developing an OPEX based machine learning model or defining machines which have capabilities of smartly giving a solution which can provide predictive or prescriptive faults in its own manner in order to solve the problem and make sure that any of these cable lines are not failing in real time, and the health indices of these particular cable um, um, lines which have been installed in the production environments are having its own set of prescriptive outcomes so as to make sure that the overall um, power system do not go into the outage. Now, again, the question is that of all these set of cables that we are seeing in this particular segment, how many of them are comprising of power cables and control cables? Now, I'm trying to put the entire scenario from both the markets, from the power and the control cable, because at the end, what happens is that we are trying to see it not only from the digitized point of view, but to see that how exactly any utility customer, for instance, are interested is slash are interested in order to install a machine learning based solution and make sure that their OPEXs are reduced as much as possible and increase their return of investments. So if you can see, out of the 100%, around 87% of the entire cable lines are power cables. And that's pretty much sure, right? I'm like, control cables have been into existence from what, maybe roughly sometime when it comes to the power cable installations. So what has happened is that over the time, the power cables, being in the legacy from God knows when, has kept its market stagnant when it comes to making more and more set of assets in coming into picture and connecting different newer ideas like having integrating the solar PV panels or wind turbines. They all come into existence with a single set of cables which the technology of which has been slowly and steadily propagated over the time. Okay, having said that, and considering that the installation of newer set of cables are going to be one of the lead markets in the day, anyone in this particular sector wants to monitor them 24 cross 7 and cross 6 365. While why? Because of the very fact that all these cables come with their own remaining useful lives, or the aging factor which do comes to any assets in itself. In which case, any customer who is installing any IoT sensors for its real-time moments would want to know ABCD. Now, what are these ABCD and why they are important? Again, with a booming market of around 250 billion US dollars, you can expect that even 1% of the cables which are going through a fault or a failure might be expecting their real-time monitoring and health indexing so that any faults which are happening in real time could be solved proactively. Okay. So if you are a customer and you want to go for a solution which is given by, let's say, OrxaGrid, what are the different set of questions that you should ask, or we know that these set of questions do come to OrxaGrid customers? So definitely we need to know what are the sources from where the data is going to be fetched. Is it going to be processing of the data from, let's say, MySQLs, or is it coming from the Azure databases, or is it coming from Oracle or MongoDBs, or what? On the basis of which the entire solution gets developed. Either you'll be having a solution which is already present. If not, from scratch, if we want to define a solution, we give out a set of data sources from which you can pull the data. But then again, when it comes to the solutions which are already available in the market, like for instance, OPC. OPC servers are already existent in the renewable sector. So when you are belonging to that particular segment of OPC servers, you will be definitely looking into the solutions which can directly integrate to these servers, and from there pull the data, provide you the health indexing related fundamentals which a machine could probably learn over the time, and tell you proactively that okay, this is the day when you can expect a fault with a probability of, let's say, 70% or 80% or so. And hence the solution should be scalable, should be compliant to multiple set of sources from which the data can be pulled and can be integrated, so that the set of KPIs that have been mentioned can be given to the customer and they can make meaningful insights out of it. Having said that, once you acquire the data, you want to do classifications in terms of age using the metadata or the insulation conditions. Apart from that, you map the cable sections onto secondary substations and feeders using the geographical data. Again, let's say if you are falling into a particular condition where the cable sections are having a water body nearby, let's say a river or a lake or something, you can expect a straightforward ingress kind of a problem which would have exist to these kind of cable sections or feeders. In which case, you'd necessarily need to know that where exactly the water bodies are lying in the vicinity. And hence, a set of geographical information given to AI/ML service provider or the artificial intelligence machine learning provider can make meaningful insights out of it and tell you that okay, there is a possibility that a certain feeder line or a cable section might go into an ingress kind of a fault. Okay, when you do that from the geographical data and the electrical data which have been given to you or you have acquired using your own IoT sensors, you definitely want to understand that what are the set of faults that these cable lines would necessarily get into. What is the structuralization of these particular fault in the history? You might have seen, let's say, a PD fault or let's say a joint failure in the past. But then, if I want to structurize and speak about that, okay, in a trend analysis, these particular set of faults fall into a certain set of category. Let's say in the 6 months down the 6 months of line or in the 3 months of frequency, then that is something which is important when it comes to acquiring the data from the real-time sensors. Again, analyze the relationship. So you can, you once you have structurized your data, you have analyzed the faults which have happened into a feeder line or a cable line. You want to understand that what is the difference between what it was actually sourcing to versus what is the overall specifications that have been given to that particular feeder line. Of course, right? I mean, like, if you can understand what is the optimum utilization which is being made to that cable section, you can definitely make sure that you know how much amount of percentage loading you can keep for that particular feeder line. Again, having said that, you want to understand what is the power quality parameter like voltage Saxwell, which happens to a particular feeder line, right? Again, solving the set of parameters that we have mentioned in the first few lines, you would want to give a prescriptive solutions using prescriptive maintenance models. Now, what are these? As we spoke in our last call or in our last webinar, we said that there are descriptive solutions, we have predictive solutions, and now we are going and moving more towards prescriptive solutions. Now, what are prescriptive solutions? The models in itself, when they are capturing the data from a cable or a feeder line, should necessarily not only tell you that there is a possibility of a PD fault that is going to happen to a feeder line, but also should tell you that what should be the set of actions that should be defined for an O&M person who is on site so as to make sure that the feeder line does not go into a fault or a failure. For instance, if we are using a PD kit which has been provided by Scope, that is a set of toolkit which would be prescribed by the model given by OrxaGrid as a solution in itself, as a prescriptive solution or a prescriptive maintenance model. And hence, whenever you go and you try to hunt for a model which is going to give you a solution which is going to be proactive, it should not be just a predictive outcome, but it should also be giving you toolkit in order to make sure that the solution is not just specific to providing a predictive output, but telling you what you should do if in case that particular failure or a fault happens. Again, one of the things which we have normally seen in our past with experiences with our clients is that we try to make sure that we discuss and validate our technical approaches with our customer through a feedback in order to make sure that any solution that we give is being happily verified and validated by our customers. If not, then it is just something which happens to be working in an open loop and does not have necessarily definitive outputs out of the same. And hence, the customer engagement in itself is something which is more important when it comes to giving or getting a project which is in the domain of machine learning. Again, OrxaGrid is an IIoT manufacturing company, IIoT and web SCADA manufacturing company. But when it comes to the additional sensors which go in line, for instance, if I want to add an additional temperature sensor, or I want to add any geological sensor, so as to make sure that I know that, okay, what are the additional parameters which are implying onto the cable or the feeder line health, then these kind of additional sensors should also be suggested by the subject matter expertise that do come out of the machine learning model and the team that works along with it. And hence, whenever a customer looks out for a solution, they should definitely, or he or she definitely looks out for a solution which is being backed up by a company which has the DNA of the domain in which the project is being given. For instance, for this particular case, OrxaGrid has a DNA of electrical engineering, which comes from Scope, which is working in the same domain from the past 35 years on. So any solution which OrxaGrid gives is backed up by the subject matter expertise that we have built along our 35 years of age into our solutions of machine learning and AI in order to tune it and give you actionable and meaningful insights rather than giving you solutions which are just meant and built on a data science based model. Because data science models or ML models, they don't have the capability to mm, learn things by themselves. Like I would say, they might learn 90% of the things by the algorithms which are existing in the literature and on the open source or the tools that are available on the internet. But that remaining 10% definitely comes by the subject matter expertise, where the maximum decisions or the investments in any of the feeder line companies or utilities go, making sure that any investment that you do has a meaningful return on investments and a payback. Okay, so having spoken about what customers require, if I have to quickly put it down into set of dimensions which we do, try to comply with our customers and customers do ask for, are getting the capable metadata, grid data, technical data, which talks about what is going to be the health of the given feeder line. History, of course, we do want to understand that what fault happened and what was the underlying electrical and ABC parameters. So we need to understand what is the fault history. And again, when it talk about the real-time solution, which has to be given on the prescription basis, we need to understand what are its real-time electrical and temperature parameters, which means that any SCADA parameter like the ones which are given in 5 minutes interval or 1 minute interval or so, which allows us to give you actionable insights on to failures and reliabilities. Okay. So after getting the set of requirements from the customers and having mapped everything to the data sets which we are going to acquire either through our IoT solutions or the solutions that are being already installed given by the customer themselves, there has to be set of um, um, actionable plan which is to be given to the customer. For instance, what do we do? At OrxaGrid, we do a kickoff by getting the data or the data acquisition, which is normally done. We have our own sensors called as seed, which we did speak about in our last webinar, which have the capability of getting all the relevant parameters from the electrical feeder lines or the cable lines. And then from the basis of the data acquisition, which is made from the seed sensors towards the gap software which we have, we do feature engineering, which is one of the most important steps when it comes to the solution which we want to be specific to a particular fault or a failure which we are looking into. And hence, trying to remove the garbage data, defining the features, or preparing the set of feature sets for developing a model is something which is most important thing and eats out around 80% of your time when it comes to the development of a machine learning model. So we try to make sure that whatever data we get is not just garbage or having some set of communication issues or detachments, and only the data which has purity in it, like around removing the anomalies and all these kind of things, is then fed to the model, which is a machine which is built either out of neural nets or decision trees or statistical models or risk assessment models, and then the model tries to learn only from the data which has its own credibilities. So then we develop the model, and on the basis of the model that is being developed, we try to give you hypotheses which are the outcomes of the model, telling you that possibilities of a fault, let's say a PD fault, happening in the future in the next 15 days or so is, let's say, 70%. So I'll tell you, or the OrxaGrid models will tell you that a PD fault on a cable line is going to happen in the next 15 days with a probability of 80% or 90% on the basis of the data which is being developed. If the data is pure, raw in itself, having no garbage or no anomalies in itself, then we have a higher accuracies which do happen to be more accurate when it comes to O&M that is happening on site. If not, the probability of failure lowers down. So what we are trying to show in the red box over here, we call it as a POC stage in which we try to give you a model which is based on a proof of concept. Once we give you a model which is proving its capabilities and you can actually verify and validate it on site, then we ask for the customers for a feedback in order to make sure that it can be moved to a minimum viable product or an MVP. In the MVP stage, we try to convert that particular model and the hypothesis which we have given to you, along with the feedback which the utilities give, into set of prescriptions and integrate it into the software which we have in order to make sure that the customer enjoys all the set of utilities which are given in the gap software, which is having its own set of benefits when it comes to optimization in energy and power. And hence, we give you prescriptions. And once an MVP stage is over, we try to roll out the features and the features or the utilities which do go into the gap software, like integrating these models into the software, upgrading these models as we go. For instance, it might happen that I might give you prediction on the joint failure in the cable fault, and there might be a possibility that along the probability of failure of around 80%, you don't find a joint failure in reality, which happens to be a feedback to the models in real time, which is given to the model, and they retune themselves, and as a software development lifecycle, we try to convert them into versioning. During the versions, you understand that okay, with every patch which we install, the overall accuracy of the model becomes more and more towards uh, ground truth, because it has started seeing the actual premise faults that have happened in the pipeline, right? And hence, what happens is that it keeps on tuning, and at one stage, it becomes so synced with the reality that the customer also enjoys the benefits out of it, reducing their OPEX costs, and the model in itself gives you the accuracies which you desire. So that's the overall syncing that we try to do when it comes to the models that we try to build along with our customers. Again, restating the hypotheses and model development in the utility systems is something which is an obvious implicative outcome. Okay, this is something that you'll very straightforwardly find out in the literature when you try to search for what the machine learning in itself is. But if I have to quickly recap you through or tell you that what exactly these models do and what are the set of strategies that we deploy when it comes to deploying any model in the machine learning domain itself. I mean, it is not restricted to cables, but if I have to, if I have to fixate myself and try to see it from the perspective of defining a fault for a cable line, this is what I will do. So you'll find a initial data set either captured from the IIoT sensors seed, which we do install in the line. Then we do exploratory data analysis, which is defining the features or PCAs and SOM. Then we do data cleaning, data curation, removal of the redundancy features or anomaly extractions, so that the overall feature set is free of any issues in itself, and you get a pre-processed data set which is which is then made accessible to your models, and then the model can easily train on themselves in order to be more accurate and be free of any anomalies in itself. Once the pre-processed data set is available, we split the data set into 80-20%, which is like a normal rule in the data science field itself, of defining a training set and a testing set, defining the hyperparameters, defining the set of algorithms that you want to deploy. It could be SVM, it could be deep learning networks, or it could be random forests or KNN or whatnot. And on the basis of which you define your KPIs, which are then made available for validation. Once you have a trained model and you have validated its metrics, then you want to understand that what are the predictions that they are given. Again, when it comes to cable health, let's say your feeder line, which has already been installed in the line, is having an actual cable health of 3 out of 5. And my model is telling you 4 out of 5. So there is a delta of 1 between the two, right? But for the model to learn itself, it needs to have a historical data available to them, so that on the basis of which it will say that, okay, the overall accuracy of the model is this much. And you can rely on this model and make sure that the overall output is somewhere near, or the predictions are near to the ground reality. So we make predictions in 3 sectors. You have a training set where you will be making predictions. Sorry, you have a testing set where you will be making the predictions and you will be confirming what is the accuracy of the model. You predict these and make sure that, okay, it is actually being confined to the set of experience data that has been given to you. And then on the basis of the two, training and the testing and the confinement that you do, you define that what is going to be the actual reality in the coming future. And that coming future scenario that I'm speaking of, where you define that, okay, boss, my training model is telling you that in the next 15 days there is a possibility of a joint failure. Then you have to be living in the future where you try to define that, okay, in the next 15 days, am I actually seeing a fault in that case or not? Definitely, you don't have to wait for the fault to happen. But this is an indicative that, okay, a certain feeder line is going to go in a fault, which means you try to trigger your O&M activities in order to make sure that that fault does not happen and your OPEXs can be reduced. Again, the question is, how can you be sure of a model that has been only trained on a set of data set which is coming through, let's say, 6 months or 12 months or so? In which case, you have to keep working with the feedback loop and keep on a complete focus on the probability of failures that we give you along with the train model that we have. It will tell you that the overall probability of failure, which I'm saying that is going to be a joint failure in the next coming 15 days, is going to be 60%. If it is 60%, it means that the probability is little bit higher and you need not take very drastic steps in order to make sure that the cables are not going into failure. But you can make sure that you take some precautionary measures in order to make sure that the cable is not going into a failure or a fault. But if I tell you that the overall probability of failure is somewhere around 80 or 90%, it means that it is calling for an SOS for the O&M people to actually go on site and make sure that there are no stones unturned and the cable or the feeder line is made sure of no faults or failure. Okay, that is something. I mean, in the previous slide is something which is already you can you can correlate it if any of the data science people who are watching this particular webinar, you can actually correlate it with what you have learned in your data science basics. But when it comes to ground reality, what I'm showing you on the screen are the actual real-time data sets which we try to solve the in the cable or the feeder line sections itself. What we do is that we take the data set, we define the weightages of the features, and on the basis of the features, we then give it to our machine learning models, which try to predict the faults which do happen in real time. What you're seeing on the top are the actual faults versus what the solution predicted. And it can be seen that the overall accuracy is somewhere around 80 to 90%. So that is how the model propagates. You have to take the data, you have to define the importance of the feature. For instance, from the feeder line, if you take voltage and current data, if you take the length of the cable, or if you take the type of the cable, these are more important features to me. Not only me, I mean, I'm speaking about the machine learning models. But when it comes to a logical set of mind, and I try to see that, okay, are the cable IDs or section IDs, or let's say, for instance, whether they are having a particular voltage parameter or a certain uh, identification parameter like a metadata, which is not related to their electrical loading in itself. I mean, definitely voltages would be something which would be important, but a section name or a feeder name is not something which is going to tell me whether a particular model is going to be failing or not. Now, when I do talk about a module which is going to fail, in this case, module is nothing but a feeder line or a cable line, right? So if I say that if a cable line or a feeder line is going to fail, the important factor is going to be its electrical parameters rather than its metadata parameters like name or something. Again, name is important when you are going to predict the future. But in the place where you are going to train the models, the most important parameter which it comes into existence is /r. It's electrical parameters, or the parameters which are going to define its possibility of a fault. Okay, this is something which I was speaking about when I talked about the geographical information systems, or the GIS. You can define your health indices on the basis of the parameters that do come from the IIoT sensors, like I said about seed. But then some of the parameters are not direct, they are implicative. When I say implicative, one of the examples that I gave before is about how ingress can be one of the situations where you can expect a fault. Now, in order to build the ingress into the system, you need to be sure of the fact that okay, where the water bodies are lying. If you want to understand where the water bodies are lying, one of the easiest way to get this mapped into your system is implementing the Google Maps or Open Maps or anything of that sort, which allows you to understand that where exactly the location of a water body is vis-a-vis the placements of the cable or the feeder lines. So what do we do in OrxaGrid is that additionally we give you a layer of getting the geographical information from the feeder lines from a map or a software like a QGIS or a quantum GIS, where you have the capability of understanding not only from the electrical parameters that are being extracted by an IIoT sensor like SEED, but also from the physical or the geographical understanding of where exactly the feeder lines have been closed. Many a times we get this particular requirement from the customers saying that the possibilities of XYZ fault is almost zero, but then it's not just the electrical parameters which give you the insight, but the actual ambience which allows you to understand what exactly went wrong in your feeder line, which is the place where we try to recommend our customers that okay, you can get the GIS information, feed it to our software, and our software will intelligently tell you that where direct faults are implicated. Use that data, define an asset health index, and on the basis of which you can probably yeah, with a probability of failure, you can define that okay, there is a prediction or a prescription of a failure which is going to happen in the next 15 to 30 days. Okay, this is one of the, apart from the few things which I mentioned in the previous slides, this is one of the legacy which comes to us directly from the company scope, which, as I told you before, which already has its own TNM instruments available with them, which allows us to feed the data from the frequently offline measurements and TNM, which has been done by the customers in the utility, take that data, integrate it into our software, and correct the value of health devices. Many a times it so happens that some of the faults which you see are not just implicative of the current and voltage parameters that you see in real time. They do happen to be more evident when you try to take the device offline and try to perform an actual extreme test on the device in order to understand whether a fault is already existing or not. That's number one. Number two, imagine if a fault has already occurred into a feeder line. If it has occurred, possibilities of similar set of fault happening in the vicinity is high. And hence, you would try to understand what were the geographical issues that might have caused that fault. One of the easiest and straightforward way of implementing this is something called as a traveling wave fault locator or a TWFL, where you can insert a search which gets reflected from the place of fault where from the place of fault in the feeder line in order to understand that where exactly the fault in the feeder line is happening. Again, this is an offline instrument, but then getting that data, integrating into the software which we have on the OrxaGrid side, allows you to be more specific and more accurate towards predicting any set of failures that happen in a feeder or a cable line. Now, if you might be knowing, we already have our TWFL instrument called as cable test van or cable fault locator van or CFL van, which we do sell it on our scope side. They have the capability of getting all the data over the internet or a web server or a web client. You can imagine that the overall infrastructure is easily accessible and compatible in order to integrate the data right from the web services via a firewall into the gap software. So the possibilities of integrating such solutions which are available in the market and are frequently used in the offline side is something which has been made available into our OrxaGrid software. Now, what I want to convey is the solutions which we give on our scope side, which are going to be on, which are necessarily on the offline TLM solutions. These happen to be a point of accessibility or propagation, where we try to make sure that these set of data are also making sure that any predictions and prescriptions that you give are more specific towards real-time faults which are or near reality. So it should not happen that the prescriptions that the model that we are giving you from the OrxaGrid side are not being verified with the ground truth, and which is where the offline solutions do come in handy and try to make sure that okay, the solutions have a probability of failure which is near 80 to 90%. Okay, then what are the bottlenecks? Having spoken about what are the failures, how do you want to tackle them, how and what are the set of issues that you could possibly face when you try to solve a problem, is something which becomes very evident, right? So the bottlenecks which you could possibly face are that either you have feeder lines which have high potential, high ratings, but you don't have, or you have very few real-time sensors which are already implemented. The data that you are giving us might be having gaps, the communication failures, or the sensor in itself is not showing exact data, and the sensors are actually not calibrated. In which case, you might get unstructured data. You might get data which is not integrated into the database, like geographical or GIS solutions, which are not direct integrations which are done by the utility. Network structures that do change over time. Like it might happen that the feeder line which has been given to the AIML OEMs like OrxaGrid have been for certain cable ID, but then in the reality, when I see it on the line, the mappings are not the same. In which case, any predictions that I do for the feeder line A will be definitely wrong or inaccurate when it comes to applying it to network B. Deharmonized databases again. Okay, so when it comes to connecting the faults which are happening in the pipeline and to the SAP systems or the CRM systems which we have, or the ERM systems which we have, is something which is again a challenge, because all the fault ordering goes via SAP into the intervention systems in any utility. But if they are not connected with a common primary key, then in that case, you might fall into a problem where the model development in itself would be a deharmonized kind of a solution. Unsystemized data collection, some of the readings that are available, they might not be exactly connected to the fault which has occurred. It might be a possibility that you have captured the data, but then the data is not relevant when it comes to the fault which has actually happened in the line. So for instance, if I say a PD fault happened, I would require the data which is somewhere 6 months back, like it is historical. But if you give me data which is maybe at the time or after the fault has occurred, it might not be that systematic when it comes to the development of the models. Okay, a few faults. I mean, this is kind of a Hilbert's problem, right? You have many data sets available, but the faults which you can actually associate it with is or are very less. In which case, if the data volume is very low, the machines don't learn with accuracies which are commendable. Okay, speaking about the bottlenecks, any of the OrxaGrid solutions which we try to give from scratch, as I said before, they are definitive when it comes to giving additional sensors which are required or additional solutions which are required in order to make sure that the solution is being given in harmony to health indexing and the fault and failure probabilities. If not, we provide you solutions so that the bottlenecks that have been mentioned in the previous slide, they are being catered to. Once you do that, the entire data is then integrated into the gap dashboards, which do look like this. We do give you risk matrices, heat maps, network tables, the possibilities of failure, so that any O&M who has installed this software in their premise or are using this via a web solution can have real-time information of which cable or the section line is having problems in real time, and can define which of their O&M activities to be conducted in chronology. Okay. Having said that, the outlook gets extended towards the idea of asset management that we discussed in our last webinar. The idea is simple. You have assets in the pipeline, for instance, the cable health. Now I'm just generalizing it from the different set of dashboards that we give to our customers, considering any asset for that matter. We give you health indices. We give you 6 monthly indication of what exactly went wrong with a certain asset. Now, what you're seeing on the screen is definitely for a transformer, but if you can understand, these are generic dashboards. They get replicated to any asset for that matter. It could be cables, circuit breakers, inverters, nozzle of a wind turbine or PV string or anything for that matter. So with a cable, if you get the gap dashboards from OrxaGrid, we'll be giving you 6 monthly health indices, 6 monthly events of what was predicted by OrxaGrid versus what actually happened in the field reality. We give you return of investments. We give you remaining useful lives. We give you failure, malfunctions, faults, and aging, accelerations on the aging. We give you prescriptions in terms of either you require replacement or maintenance. Having said that, any investments which the higher management is looking into, they know at every point of time when they start a project with OrxaGrid that how this particular project is progressing in terms of the investments that they have done. When it comes to the CXO level people who are trying to quantify that how the project has went across the reduction in the OPEXs, this is the place where we try to make them realize that how beneficial the OrxaGrid solutions are. It's not just beneficial. I mean, if the utility is seeing it from the perspective of any solution in that case, which is going also from a fallback, they would be readily seen in black and white from these dashboards. Then what are the remaining useful life across 6 months? What are the units? What are the downtimes? What are the aging predictions? Is everything is something which you can actually see it in real time. This allows any investments that you're trying to do in the um, assets in the pipeline, along with the software solutions that you're buying, maybe it is SaaS or it is a lump sum solution or it is something which you have invested on a recurring format. You understand that what that solution is giving you versus the OEM from which you have bought the product and installed it in the substation or in the pipeline. Okay, these are some of the additional charts that we give from the technical point of view, failure fault predictions and averted failure faults across the asset health radar. Then the health indices, the cost that has been averted, how much amount of money you were able to save, how much amount of downtime you were able to save, the accelerated aging and whatnot. Apart from that, we do give you the computerized maintenance management system. These are the systems which allow you to take actions and make sure that any event for that matter is being lodged into the system for the future references. By this, you can track what went wrong, how it went wrong, what was the predictions, what was the actual ground truth, how many of the units you lost. It's like giving you an entire look and feel of how the entire asset is being tracked. Now, what I'll do is I'll quickly show you the software that we have it on our Gap site and how does it look like. My apologies, but I'll just stop presenting for a moment. Okay, Sanket, can you just confirm if it is visible?
Yes.
Okay, great. So this is the Gap software which we have. And what I'll try to show you is the set of utilities that we do provide to our customers and the asset management dashboards which are or which do come handy when it comes to the different assets which we do provide and can be taken benefits from. So this is the live dashboards. You can actually click and feel every particular item which is available over here, and on the basis of which you can take necessary actions in the ONM side of it. Now, you can see that if I do talk about cable specific particulars in the dashboard, they are more towards maintenance and replacement, and the same goes for the set of utilities. Now, the point that I want to make over here is how all the assets in a substation or in the utility can be made under a single canopy of product, which is the Gap software. It could be cable, it could be circuit breaker, inverter, as I was mentioning before. And hence, what happens is that if you are buying any set of products from different set of customers or OEMs, you can see the entire track of all these products and they're working in at a single place. Again, if you want to add all the offline instruments into a single canopy, you can also do that. You can add all the TNM references like the cable fault locator and related services that you actually want into a single dashboard and see that how exactly they perform when it comes to the cable health indexing. Okay, one more thing that is implicative when it comes to any utility in itself or an IPP that they do want to understand what are the prescriptions and the toolkits. So we give you the prescriptions on either you require a maintenance or a replacement, and along with that, whether there are recommended tests that are required or the toolkits which are required for a certain asset in that uh, situation. For instance, you can use a CFL and apply a TWFL, or if there is a possibility of a PD failure, we do recommend uh, our TNM solutions for the same. Okay, getting back, these are some of my references, and that is what I wanted to say about this particular webinar. Um, I hope you guys got a good amount of knowledge out of it. You can always write back to me. Okay, over to you, Sanket, if there are any questions. Hello, Sanket.
There are no questions as such as of now. Uh, I'll ask everyone to fill up the feedback form so that we can also learn something from it. Doctor, thank you. It has been an outstanding session because we have learned a lot from it today. How the test and measuring instrument can help us get some get more data as of now. So this is something which is very important for us to understand and keep it as a note that every time we do a testing and if we record that data, it would be always helpful, isn't it?
Yeah, yeah.
We'll wait for a few minutes. If anyone has any questions, they can now put on their mic and ask a question. That's not a problem. You can turn on your mic and ask the question. By the meantime, I'm just putting the this thing up, recording. Just hold on.
Yeah.